Here's section 3.3, exercise 48. This one definitely starts to get a bit interesting. We get f of x is equal to sine of x over 1 plus cosine squared x. And again, we are on the interval 0 to 2 pi, the open interval 0 to 2 pi. Let's see, so we take the derivative. This is not looking fun. Derivative top is cosine of x, and then times the 1 plus cosine squared x minus the top times the derivative of 1 plus cosine squared. So, well, the 1 just becomes a 0. But I get my 2 cosine x, but then times negative sine x because of the chain rule. So, whoa. That looks really nasty. And then all over 1 plus cosine squared x, all squared. Now the nice part is the bottom is squared, and it only takes the top to make this thing 0, and so the bottom is fine. This is not undefined anywhere in that I'm never dividing by 0 because I'm taking cosine squared. So cosine squared is never negative, so when I add 1, I always have a positive number, and then I square it. So this derivative's not undefined anywhere. But it looks pretty screwy here. So, I don't know, multiplying some things out, right? I get cosine of x plus cosine cubed x minus, well, wait, minus and a minus make a plus. So plus 2 sine squared x cosine x. Okay, so this is somewhat helpful because I can, out of every term, I can factor out a cosine of x. So this is cosine of x times 1 plus cosine squared x plus 2 sine squared x. Now, so one nice part is, okay, one of the places that the derivative will be 0 is when cosine x is 0. Great. But the other is when 1 plus cosine squared x plus 2 sine squared x is equal to 0. Now that looks pretty bad at first, but again, I remember some trig identities, and so I can take one of those sine squareds and put it with that cosine squared and make that 1. So this actually is 2 plus sine squared x is equal to 0. And there are a couple things that point out to me, oh, this is actually never 0. One is I've got 2 plus a non-negative number. Well, so that's always going to be positive, can't be 0. Another is that if I did move the 2 to the other side, I would have sine squared x equals negative 2. Well, I can't have a square being negative 2, so there's another one. But then if I were still silly enough to keep going, and I thought about taking a square root or something, well, the square root of 2, or, well, negative 2 is undefined in real numbers, but the square root of 2 is bigger than 1, and sine can never be bigger than 1. And so there are all kinds of things that tell me, yeah, this side's never 0. And so we just have, well, whenever cosine x is 0, and that is at x equal pi over 2 and at 3 pi over 2. And so I just have those two critical numbers. So these are my critical numbers. So this could have been really nasty, and I could have really needed technology to get this, but it's a book problem. They tend to make problems that work out nicely. I mean, even if they're a little ugly, hey, this one not so bad compared to what it was looking like. And so, I'm going to look here between 0, pi over 2, 3 pi over 2, and then 2 pi. And again, as I look at that derivative, so, I have this whole derivative. Oh, and I put an equals here. I'm sorry. That was, if you do that, I'll make fun of you. You should make fun of me. I should have said implies. Okay, why implies not equal? Well, because I got rid of the denominator there. So they weren't equal. But this, or it flows from this first thing here when I just look at the numerator that I have that. Now, this equal is okay because this here is indeed equal to that. So I apologize for writing the equal sign. Again, in retrospect, when I went back, I noticed it. Okay, so you still can make fun of me and all that. But yeah, I should not have had an equal sign there. Should have just had some kind of implication error or written some English or something like that. And so let me rewrite the f prime though. So, f prime of x is the cosine of x times, and remember on this, I simplified that to be the times 2 plus sine squared x, and then over something that's squared. So again, there it's over that thing. So it's over something that's squared. The thing is, I don't really care what the value is other than is it positive or negative. Well, see, this is always bigger than 0 down here. This thing in here is always bigger than 0, 2 plus sine squared x. And so it's just about the cosine. And between 0 and pi over 2, then f prime is positive because the cosine is positive. So there's a positive. Then between pi over 2 and 3 pi over 2, cosine is negative. And so f prime is going to be negative. And then between 3 pi over 2 and 2 pi, the cosine is positive again. So f prime is positive. And if I kind of redraw this real quick, 0, pi over 2, 3 pi over 2, and 2 pi, what we see is that was positive, that was negative, that was positive. Okay, so we have everything's defined, so this is a relative max at pi over 2, and we have a relative min at 3 pi over 2. So again, let's go check that. Now there, the red, oops, got my pen too close. The red, that is one, I don't know why that moves when I get my pen there. Sorry. Okay. So, so here's the red is our function, and man, that's wiggly. But notice, yep, we have a relative max there at pi over 2, and we have a relative min there at 3 pi over 2. Great. And it was decreasing in between and increasing, at the two ends. But look at that. The blue is the derivative. Look at what that derivative is doing. It's going all over the place. Now, but it definitely, is 0 at pi over 2 and 0 at 3 pi over 2. And so in positive to the left between 0 and pi over 2. and negative in between, and so forth. So we got that right. But look at, that's one messed up function right there. That's looking mighty nasty. But that is number 48.